Hey there, this is the video for Chapter 7, Section 2. This section is continuing right where we left off last section. You will need your calculator and or the standard normal table for this section, so make sure you have those handy. We'll be using two different functions on the calculator, the normal CDF and the inverse norm functions, so you might want to refamiliarize yourself with those. One is going to give us area given lower and upper bounds. The other is going to give us a z-score given area. So besides needing it for this section, it's actually really good practice to know how to go back and forth between them. There's a note for you in the lecture notes for this section that has some information that will help you in the future so you don't have to type everything into the calculator. You'll know it when you see it. It has to do with output values. Okay, so we're also going to have lots of multiple instructions for the steps to go through the testing. We're gathering a bunch of those, aren't we? Okay, let's get started. Hi guys, this is an edited, small added section. Just a quick note before we dive in. I apologize, but at some point during this video I misspoke and said there was only one more section left in this chapter. I'm sorry, but that's not actually true. There are two more sections. Didn't want to get your hopes up, and didn't want to confuse you. I believe I also found an error where I skipped a line during one of the exercises, but I figured you guys are adults and could follow along. Professors aren't perfect. We're human too. I don't mind admitting that I make mistakes. Mistakes are opportunities to learn. Okay, back to your regularly scheduled program. Welcome to the lecture video for Chapter 7, Section 2, Hypothesis Testing for the Mean when Sigma is Known. Here's what we're going to be going over today. We're going to learn how to find and interpret p-values. We're going to learn how to use those values for a z-test for a mean mu when sigma is known. You'll learn how to find critical values in what are called rejection regions in the standard normal distribution, and how to use rejection regions for a z-test for a mean mu when sigma is known. Okay, let's get to it. So we left off last time with this idea of comparing a p-value to a level of significance, which we said would typically be 10%, 5%, or 1%, and is represented by the lowercase Greek letter alpha. And this level of significance represents the bounds within which values that are very unusual would be found. So when we're making decisions about hypothesis tests, and we come across a p-value that is smaller than or equal to an alpha, or level of significance, we want to reject the hypothesis test, or H0, because that means it's existing in the very unusual space outside the norm, and our evidence is strong enough that we can reject it. But if p is greater than alpha, then our evidence is not strong enough and we fail to reject H0. Remember, we're not accepting anything for these, it's all about rejecting or failing to reject. So if we don't reject it, we fail to reject it. Okay, to make sure we're understanding this part, let's do an example. The p-value for a hypothesis test is p equals 0.0237. What is your decision if the level of significance is number 1, alpha equals 0.05. Think about this. Alpha is 0.05 or 5%. So that's what we're comparing to. That's our outer bounds, our low number we're comparing against. So what you ask is 0.0237 less than 0.05? Yes, it is less than 0.05. So what do we do in this case? We reject the null hypothesis. Remember, the evidence is strong enough for us to do that when it is lower than or equal to the level of significance. Okay, next one. The p level is the same. It is p equals 0.0237, but this time alpha equals 0.01. What is our decision? Our question is 0.0237 less than 0.01? No, it is not less than 0.01. So what do we do in this case? Well, we fail to reject the null hypothesis. We do not have the evidence to support rejecting the hypothesis in this case. Another thing we touched upon was the nature of the hypothesis test, which depended on the alternative hypothesis. After determining the hypothesis test's standardized test statistic and the test statistic's corresponding area, we did one of the following to find the p-value. For a left-tailed test, p equals area in the left tail. This happened when h sub a was mu less than k. And for a right-tailed test, P equals area in the right tail. This happened when H sub A was mu greater than K. And for a two-tailed test, P equals area in both tails. This happened when H sub A was mu was not equal to K. Let's do a few examples. Find the p-value for a left-tailed hypothesis with a test statistic of z equals negative 2.23. Decide whether to reject H0 when the level of significance is alpha equals 0.01. Well, they're telling us that it's a left-tailed test, and they gave us the p-value. So we can draw our graph and place the standardized test statistic. Now we need the area, so we can compare it to the level of significance of alpha equals 0.01. We can do that with the table by looking up negative 2.23, or we can use the normal CDF function on our calculator, with a large negative number as the lower bound, and the negative 2.23 as the upper bound. Both should give you 0.0129, which is the area in the left tail. That is the number we compare to 0.01. So let's compare it. Is 0.0129 smaller than 0.01? No, it's not. So that means we failed to reject the hypothesis. And that's how you should approach all of these. Find the area, ask if it's smaller than the significance level in decimal form. If it's not, fail to reject. If it is, reject. Okay, let's do another. Find the p-value for a two-tailed hypothesis test with a test statistic of z equals 2.14. Decide whether to reject H0 when the level of significance is alpha equals 0.05. So a two-tailed hypothesis test means that I'm going to have two places where the test statistic lies. One negative and one positive, with area filled in to the left and right of them. I know these are symmetric, and I know I can figure out the negative area, so I figure one out. I can multiply by 2 to get the value for total area, which is what we need for the p-value. Because remember, half of the p-value is on each side. First, using the calculator, let's use the normal CDF function and a large negative lower bound and negative 2.14. If you don't remember how to do that, that is the second button, then the vars button. Then you put in lower value, and in order to put a large negative number, you put the negative sign, then 1, then second, then the comma, and then 99, and that gives you your large lower. Then you're going to press enter. Then you're going to put in 2.14 as your upper bound. Okay, and then press enter as many times as you need to calculate. And we should come up with 0.0162. Now, an important part about this is that we need to multiply that by 2, because that is just one side. So when we multiply that by 2, we get 0.0324. So that's our p-value, or our total area, 0.0324. And that's the number we compare to alpha, which was 0.05. So then we ask the question, is 0.0324 less than 0.05? Yes, it is. So here we have the evidence to reject the null hypothesis. Remember, if it is less than the significance level area, then we have enough evidence to reject the null hypothesis. Okay, let's pull back and look at the big picture again for a moment. Where is all this coming from? We've got a population parameter, which could be mu, sigma, sigma squared, or population proportion p. We've got a parameter that someone has tried to estimate with a point estimate, and those could be x bar, s, s squared, or p hat. And we're testing whether or not their claim about the parameter can be supported. We're testing their claim. We do this by taking their test statistic and standardizing it. In other words, a z-test can be used for a mean mu when, number one, the sample used to find the test statistic has been randomly selected so that it makes it unbiased, and number two, as we've heard before, either the population itself is normally distributed or the sample size is greater than or equal to 30. So those sort of characteristics utilizing the central limit theorem haven't gone away. So look at the formula we're using here. this large formula up here at the top. This should be slightly familiar. It's very similar to the sampling distribution of sample means z-score formula. And we have the standard error of the mean with sigma divided by square root of the sample size. Okay, so how are we going to use this z-score formula? Let's go over this in words and symbols. First, we need to verify that sigma is known. Do we have a population standard deviation? Is the sample random? And is either the population normally distributed or is the sample size greater than or equal to 30? If all these check out, we then gather data we're going to need. For example, we know we're going to need sigma or standard deviation and sample size or n, so those will be important to grab. Next, I want to state my null and alternative hypothesis. You'll use the skills that you mastered in the last section to do those. Next, I want to state my level of significance, or alpha, in decimal form. Now enough information should be given in the problem for us to standardize the test statistic. Then, from H sub A, the alternative hypothesis, we should be able to graph the test. During this process, we'll be using normal CDF on the calculator or the table to find the area that corresponds to Z. During this process, we will identify the p-value. Sometimes this will be the same as the area, sometimes it will be twice the area, depending on whether we have one or two tails. After you have the area, you compare it to your alpha value. If it is less than the alpha or significance level, you reject the null hypothesis because you have enough evidence to reject it. If it is not less than alpha, you do not have enough evidence and you fail to reject the null hypothesis. Lastly, interpret the decision in the context of the original claim. Let's do an example. In auto racing, a pit stop is where a racing vehicle stops for new tires, fuel, repairs, and other mechanical adjustments. The efficiency of a pit crew that makes these adjustments can affect the outcome of a race. A pit crew claims that a mean pit stop time for 4 new tires and fuel is less than 13 seconds. A random sample of 32 pit stop times has a sample mean of 12.9 seconds. Assume the population standard deviation is 0.19 seconds. Is there enough evidence to support the claim at alpha equals 0.01? Use a p-value. Okay, so let's go through the steps. Are we given population standard deviation, or sigma? Yes, they gave us 0.19 seconds. Is the sample random? Yes, that is what they said. Is the population normally distributed, or is the sample size at least 30? It does not state that the population is normally distributed, but the sample size is 32, so we can approximate it normally. Next, I need to form my null and alternative hypothesis. The claim is the mean pit stop time is less than 13 seconds. That is an inequality, so that is the alternative hypothesis. And we will say that it is mu, because we're dealing with mean, is less than 13 seconds. That would make H naught, my null hypothesis, greater than or equal to 13 seconds. So our H naught is greater than or equal to, and our alternative is less than. Next, those are my hypothesis statements. Now I'm ready to standardize my test statistic. One thing I need to note here is that we're going to assume mu equals 13 for the formula. I have all of my information to plug into the formula for my z value. My sample mean, or x bar, was 12.9 minus mu, which was 13, because we assume that mu is true, so that's why we use that value in this formula. So my sample mean, or x bar, was 12.9 minus mu, which was 13, divided by the ratio of sigma, which was 0.19, divided by the square root of n, which was 32. We get negative 2.98. This is my standardized test statistic. Okay, let's develop a graph and see what other information we can glean from this. Because less than is the symbol in our alternative hypothesis, that means we have a left-tailed test. Because it is a left-tailed test, the p-value is equal to the area to the left of z, equals negative 2.98, as shown here. Now we use the standard normal table or the normal CDF function on our calculator, using a large negative number as our lower bound and negative 2.98 as our upper bound to find our p-value, and you should get 0.0014. Now remember, the point of this was to compare our p-value to the level of significance, which was 0.01. So we compare 0.0014 to our level of significance. Is 0.0014 less than 0.01? Yes, it is. Therefore, we should reject the null hypothesis. Remember, say the tested amount first. Ask if it's less than the level of significance. If yes, you reject the null hypothesis. That can be your order of testing these. The way we word our conclusion is, there is enough evidence at the 1% level of significance to support the claim that the mean pit stop time is less than 13 seconds. Alright, let's try another example. According to a study of U.S. homes that use heating equipment, the mean indoor temperature at night during winter is 68.3 degrees Fahrenheit. You think this information is incorrect. You randomly select 25 homes that use heating equipment in the winter, and your information tells you that the mean indoor temperature is 67.2 degrees Fahrenheit. Apparently, from past studies, you gather that there is a population standard deviation of 3.5 degrees, and the population is normally distributed. Is there enough evidence to support your claim at alpha equals 0.05? Use a p-value. Okay, so we first need to ask some questions. They are asking us to support a claim, so if this were on homework or a test or a quiz, you would know that this is testing a hypothesis, as opposed to maybe building confidence intervals or finding probabilities. This is testing hypothesis. Okay, so then we ask, is sigma known? Did they give us population standard deviation? Yes, they said it was 3.5 degrees. Is it either normally distributed population, or is the sample size larger than or equal to 30? Well, the sample size is 25, which is less than 30, but they did say the population is normally distributed, so we can proceed. Alright, next we need to state our hypothesis. What is the claim? That's what we need to identify first. Our claim is that what the study came up with is false, which means not equal to. So how do we state that? The amount we're talking about is in their original study, 68.3 degrees Fahrenheit. Also, we're dealing with mean temperature, so mu. So our claim is the alternative hypothesis because it's not equal to. So our H sub A is mu is not equal to 68.3 degrees Fahrenheit. And our H naught is mu is equal to 68.3 degrees Fahrenheit, with H sub A being our claim. They gave us the level of significance they want as 0.05. Next, we need to standardize our test statistic or find our z-value. This is where that formula comes in. So we need x bar, which was 67.2, minus mu, which was 68.3, divided by the ratio of sigma 3.5, divided by the square root of our sample size of 25. And we get about negative 1.57. Again, we have mu take on the value of 68.3 for the purposes of the formula. Now we draw our graph and get our area. Because our original alternative hypothesis was not equal to, that means this is going to be a two-tailed test. And it's going to be to the left and right of negative and positive 1.57. So then we either use the table or normal CDF function to find the area to the left or right. Now remember, because this is a two-tailed test, you still need to multiply your result by 2 to get the full area, because each side is only half of p. So our p-value is 0.1164, and that is after I have multiplied by 2. Then we ask the question, is 0.1164 less than 0.05? It is not. So we fail to reject the null hypothesis. There is not enough evidence at the 5% level of significance to support the claim that the mean indoor temperature at night during the winter is different from 68.3 degrees Fahrenheit for homes that use heating equipment. Okay, now p-value is not the only way to test whether or not we should reject the null hypothesis. There is, in fact, another way to do this. Another way to assess whether or not we can reject the null hypothesis is to determine the rejection regions of the sampling distribution, also known as the critical region. This is the range of values for which the null hypothesis is not probable. If the standardized test statistic falls within that region, the null hypothesis is rejected. A critical value, z0, separates the rejection region from the non-rejection region. You'll see problems that will say to use the rejection region method or the p-value, so you need to know how to do both. If it doesn't tell you which one and just says to figure out whether to reject or fail to reject a claim, you can use either. So how do we use this new method? First, you need to know the level of significance or alpha value. We then need to decide whether it's a left-tailed, right-tailed, or two-tailed test. You're still going to go through the process of finding a z-value, but the difference is you're not going to draw a graph with that z-value. Instead, you're going to draw a graph with your alpha value. Here are what the three different graphs would look like. The area that's being shaded is the alpha value, and that's an area. Let's look at one to understand what I mean. If the significance value they gave you is 1% and the alternative hypothesis is less than, meaning a left-tailed test, your graph would look something like this. But the area we're using is not from the regular z-score. So they gave us 1%, which would correspond to an area of 0.01. So we're kind of doing this backward. We have the area to start with instead of the z-value. So that means we can use our inverse norm function on our calculator. Let's see if we remember how to do that. So use the second button, then bars, then arrow down to or press the 3 for inverse norm function, then type in decimal form the area you're working with. In this case it would be 0.01, then press enter as many times as needed to calculate. And just a side note here about your calculator, as many times as we've done this, your calculator will hopefully already have it in there for you, but as a reminder in case it doesn't, it asks for mu and sigma on this function, and because we're approximating normally, you can assume mu is 0 and sigma is 1 for all of these. Okay, so that is going to give us the critical value, or z0, for the area of 0.01, which is negative 2.33. Let's look at finding the critical values for a two-tailed test with a level of significance of 0.05, or 5%. An important thing to remember about a two-tailed test is that you're dealing with half of alpha on each side. So you need to split the area they gave you in half before you do any figuring. So they gave us 0.05. We need to split that in half first. What is half of 0.05? 0.025. You have to be very careful with that decimal and whether you're putting a 0 in there. 0.025 is half of 0.05. So each tail is going to have an area of 0.025. So the figure we'll be looking at, if we use calculators, is 0.025. If we use the table, you're going to look at 0.025, and because one of them is to the right, we'd subtract it from 1 to get 0.975. I like working with the calculator, but if the other works for you, you'll get the right answer for that also. You'll just be coming at it from a different direction. Whatever works for you as long as you understand it and you come up with the right answer. Okay, so here's our solution. As I said, we can use our calculator, specifically our inverse norm function, to find the z0 value using 0.025, or you can use the table and you would use 0.025 and 0.975. Either way, you should get negative 1.96, and with the calculator, when we extrapolate from this that our graph is symmetric and know that our result means we can use its positive version as well, then we know we have positive 1.96 also. So our critical values are negative and positive 1.96. So the rejection regions are to the left of negative 1.96 and to the right of positive 1.96. To use the rejection region to conduct the hypothesis test, we still need to calculate the standardized test statistic z like we did before. So we're figuring it as z as before and as z0 with a significance value. Then here's how we compare them for our test. If the standardized test statistic, or regular z, is in the rejection region, meaning its graph would show up within the graph we made with our significance level, then we reject the null hypothesis. If it is not in the rejection region, then we fail to reject the null hypothesis. And that makes sense, right? If it falls within the rejection region, that means it's out of bounds. We have enough evidence that it is unusual and not within the range of probable results. You can see on these graphs what we mean. Every result that is within the shaded region results in rejecting the null hypothesis. If it falls in the tan area, or outside the rejection region, we fail to reject the null hypothesis. Okay, so let's go over in words and symbols how we do this. First, we need to make sure conditions are met. Is sigma known? Have they given us population standard deviation? Is the sample random? And is either the population normally distributed or is the sample at least 30 in size? If all of these check out, we can apply the theorem and approximate this normally. Next, we need to come up with our null and alternative hypothesis. We've talked about how to do this. You start with whichever one represents the claim, and remember it can be either one. If it's an expression that has an equality statement in it, less than or equal to, or greater than or equal to, it will be in the null hypothesis. If it's an inequality, it will go in the alternative hypothesis. Next, specify the level of significance, identify our alpha, and we need to have that in decimal form. After that, we need to find our Z0 values, our critical values. We can use the table or our calculator for this. Remember, we're using the significance level alpha as the area, and we're working backward. And you can use inverse norm function for this as well. Next, we determine the rejection regions on the graph. Then we find the standardized test statistic by using this handy formula. And we're almost done. The next thing we do is compare this found value to our area and make a decision whether to reject or fail to reject the null hypothesis. Lastly, interpret the decision in the context of the problem using the language of the original claim. Okay, let's apply all this to a problem. Employees at a construction and mining company claim that the mean salary of the company's mechanical engineers is less than that of one of its competitors, which is $95,600. A random sample of 20 of the company's mechanical engineers has a mean salary of $93,300. Assume the population standard deviation is 9,500 and the population is normally distributed. At alpha equals 0.05, test the employee's claim. Alright, so first we need to check all the conditions. Do we have sigma? Yes, they gave us 9,500. Is the sample random? Yes. Is the population normally distributed or is the sample at least 30? The sample is only 20, but they say the population is normally distributed, so we can continue with the z-test. Next, what is the claim? The claim is the mean salary is less than 95,600. So this is a less than, which is an inequality, so we're going to be writing which of our hypotheses first. If you guessed alternative hypothesis, congratulations, you're still awake. Great job. Okay, seriously, that's right. So our alternative hypothesis is mu, because we're dealing with mean. Mu is less than 95,600. The null hypothesis needs to be its complement, so that would be what? Pause the video for a moment to figure that one out. So H0 should be greater than or equal to 95,600, and H sub A should be mu is less than 95,600, and that's our claim. Okay, remember our next step? Next is specifying the level of significance. They said 0.05. From that, we get our critical value, or Z0, from the table or the calculator of negative 1.645. And so the rejection region for this one, because it's less than, is Z is less than negative 1.645. So then the standardized test statistic we find by plugging these values from the problem into our formula, and we assume the null hypothesis, which said mu is greater than or equal to 95,600 is true. When we do that, we get about negative 1.08. Let's see what that means on a graph. The shaded region is the rejection region, and the orange text shows our standardized statistic of negative 1.08. It is not in the rejection region, so we do not have sufficient evidence to reject the null hypothesis. So we fail to reject the null hypothesis. There's not enough evidence at the 5% level of significance to support the employee's claim that the mean salary is less than 95,600. Okay, let's do one more, then we'll call it for the day. Hang in there. A researcher claims that the mean annual cost of raising a child between the ages of 1 and 3 in the U.S. is $13,350. In a random sample of families in the U.S., the sample consists of 1,000 children. Assume the population standard deviation is 2750. At alpha equals 0.10, is there enough evidence to reject the claim? So we need to start by checking the conditions. Did they give us sigma, population standard deviation? Yes, it is 2750. Is the sample random? They say yes, it is. Is the population normally distributed, or is the sample greater than or equal to 30? It does not mention being normally distributed, but the sample is large at 1,000 children. So the central limit theorem comes into play. Next, we identify the claim, which is the mean annual cost is $13,350. Then we find the null and alternative hypothesis. Our claim used the word is, so that would be which hypothesis? Yes, the null hypothesis, because that is equals. So mu equals 13,350. That's our claim, and that would be the null hypothesis. So the alternative hypothesis would be mu is not equal to 13,350. After that, we identify our significance level of 0.10, and then we need to figure out our critical values of negative 1.645 and the rejection regions less than the negative of 1.645 and greater than 1.645. Then we do the standardized test statistic with the formula, again assuming that mu is equal to 13,350, and we get about negative 1.89. Alright, so let's look at the graph. Our rejection region is here, where in the blue section, where it says 0.05, because it was 10%, we had to divide that in half. When we plot our z-value on this graph, negative 1.89, you see it right here in blue, is within the rejection region on the negative side. So that means we reject the null hypothesis. So let's relate that back to the claim. It was that the mean annual cost is $13,350. So we have sufficient evidence at the 10% significance level to reject the claim that the mean annual cost of raising a child between ages 1 and 3 in the U.S. is $13,350. Okay, that was a long section with a lot of detail, but you did it. We're getting closer and closer to the end. Keep it up. Only one more section for this chapter, then just one more chapter. Okay, great job. I'll see you on the next video.